Okay, so I'm here with producer Madeleine White. Maddie, great to have you here.
Hey.
And you brought a piece of tape with you, so let's just play it and listen to what you have here.
So I'm in the washroom here at SNOLAB, and the reason why I'm taking a voice note in the washroom is because this is the furthest underground toilet in the world, and the noise it makes when you flush the toilet is quite something.
Oh my god, it's like an airplane taking off. What's happening?
Oh my god, I loved your reaction. You literally jumped in your chair.
Like, what is happening? What is that? Okay, so why were you at the toilet that is furthest underground, Maddie? How did you find yourself there?
So earlier this year, I went to SNOLAB. This is the Sudbury Neutrino Observatory Laboratory in, you guessed it, Sudbury, Ontario. And this scientific station happens to be 2 kilometers below the surface in an old mine.
Okay. And so why were you there in the first place, though?
Yeah, there are definitely more convenient bathrooms. So I didn't need to just travel 2 kilometers underground to use SNOLAB's toilet. I was there because I was trying to see how scientists are trying to unravel one of the universe's greatest mysteries, dark matter.
Okay, dark matter is one of these things I feel like I hear about and I've tried to understand, but it's hard to understand. Like, what exactly is it?
This is actually like the question. They are trying to understand what it is, because the reality is we don't really know. We don't really understand dark matter. The thing we know about dark matter is that we think it represents 85% of all the mass in the universe.
Wow. Okay, so a huge portion of the universe. But I mean, this is kind of esoteric in a way too, right, Maddie? Like, in terms of our day-to-day lives, there's a lot of other scientific problems that people are trying to solve. We just went through a pandemic, right? There's a lot of other things going on in the world. Why is it important to study something like dark matter, which we don't even really know like what it is?
Yeah, and we don't know if like knowing what it is will give us any specific benefit. For me, the pursuit of this kind of science is just about reminding us about how mysterious the universe really is and how we're just this tiny, tiny part of it. Like we're 15% of all the mass. And maybe that if, you know, this tiny fraction of all of that mass is trying to understand the universe a little bit better for the time that we have here in this universe, like maybe we will learn something about ourselves along the way.
So today, Maddie, you're going to take us on a journey to try to understand what dark matter is.
Yeah, and we're going to have to go deep underground for this hunt.
Sounds amazing. I'm Annika Raman-Wilms.
And I'm Madeleine White.
And this is The Decibel from the Globe and Mail.
It's about 5:20 in the morning. I'm here in Sudbury, Ontario, walking through a hallway of a Hilton hotel while I wait for my ride to take me to SNOLAB. I'm exhausted, but I'm really excited. And it's very quiet here in Sudbury right now. And cold and rainy. It's like 10 degrees out. Despite that, I'm dressed in spandex shorts and a t-shirt and a rain jacket because when you get 2 kilometers below the earth, I'm told it gets very hot. So yeah, I'm just hanging out here waiting for my ride. And here comes my ride. I'm going on this journey with Globe photographer and videographer Patrick Dell. Hey Patrick.
Hey Maddie.
I'm already recording.
Excellent. Nothing like wearing shorts at 5:30 in the morning.
I know. Also, it's so cold.
No, I've got the seat heating.
And science reporter Ivan Semeniuk. Hey Ivan, can you tell me where we are?
We are at the entrance to the SNOLAB physics laboratory at the Crichton Mine in Sudbury, Ontario.
SNOLAB is located just outside of Sudbury proper. If you haven't been to Sudbury, you might know it as the home of the Big Nickel, which is exactly what you think it is, literally a giant statue of a coin. Sudbury is a mining town. And SNOLAB is located inside one of the region's oldest mines. SNOLAB was originally built in the 1990s with the goal of detecting solar neutrinos and studying their behaviors. But since then, it's expanded to look for dark matter. There's a good reason why this scientific laboratory is so far underground. Here's how Dr. Jody Cooley, SNOLAB's executive director, explains it.
The reason that we're underground, it's so critical to the success of this program. And the reason is that when you're on the surface of the Earth, you're constantly being bombarded by something called a cosmic ray. It is a proton or a neutron from outer space that essentially smashes into our atmosphere and creates all sorts of other types of particles. We use the Earth as a filter to filter out those particles. And so those particles don't reach our detectors. If they did reach our detectors, they would be making noise all the time.
Getting down to the lab is its own adventure. First, we change into miner's gear because we need to be highly visible and decked out in safety equipment.
Yeah, I'm going to outfit you with a full set of mining gear. We're going to get our hard hats, our cap lamps, we'll get a set of tags, we'll get a high-vis one-piece suit, a miner's belt, and some boots and gloves.
Okay, I'm not going to lie. I look a little ridiculous here. Picture a highlighter yellow jumpsuit lined with orange reflective safety tape. I look like I was going to an underground rave dressed as a rejected member of the Village People. The last piece of equipment I'll need to get down into the mine shaft is a little unexpected. I'll let SNOLAB's Senior Communications Officer Mike Whitehouse explain.
So the air pressure changes a lot, and the remedy is the same as an airplane. Come.
Great. I noticed if you
If you're interested.
That's a great idea.
We line up in this room where miners and scientists mingle. We're all waiting for our ride down. It's a double-decker elevator called The Cage. I kid you not, it is actually referred to as the cage. If you refer to it as the elevator, you will be laughed at. It's the cage.
All right, we're going to head down.
Everyone heads down?
Okay, so I'm just walking down this ramp, fairly wide ramp, about the width of a vehicle, heading down towards the deck, and then I'm going to get into the cage to go below ground, 6,800 feet into SNOLAB. There is no door in this elevator/cage, just a metal gate to keep our limbs safely inside. As we're descending, the rock face is flashing by us. We're dropping at a speed of about 2,000 feet per minute. That's over 35 kilometers per hour. Oh, and this elevator has no lights. So, in this cage, we are standing shoulder to shoulder. That's how full it is. And it's dark. The only light is the light from somebody's headlamp standing beside me. About 5 minutes later, we're out and in a dark mining tunnel. The miners who get off with us, they get to do the rest of the journey in a tram that scoots off, leaving us literally in the dust. We, however, we get to walk.
So we're about to head down the drift.
That's Ivan again.
We have more than a kilometer to walk. We're already about 2 kilometers down. So a bit of nomenclature here. If it's a vertical movement, you're going down or up a shaft. We're moving horizontally now along the drift. So we're really only halfway through our trip.
We just passed a little room that the door was open to. and spray painted on the wall in red spray paint were in giant letters, "Please keep clean." There are other labs in the world that study dark matter, and some of them are even underground, like SNOLAB. But this lab here in Canada, under a whole bunch of Canadian shield rock, gets to hold one very specific world title. It is the cleanest, deepest scientific lab in the world. Cleanliness is a big part of SNOLAB to make sure that we don't bring any sort of particulate matter into the lab, which is very sterile. The cleanliness is not just scientists being neat freaks. It's a crucial condition for the hunt for dark matter. Because despite dark matter having a substantial effect on the universe through gravity, we think it might be incredibly tiny. And to detect something so abstractly small, you need to have as little interference as possible. Even the smallest dust particle or speck of dirt could contaminate the experiments. And to keep this level of cleanliness, there are a number of steps that we have to complete before we can actually enter SNOLAB, as Mike Whitehouse explains. And so can you explain what's about to happen next here?
So we're going to wash our boots, get all the mine dust off our boots because they are by far the most covered parts of our bodies. And then we are going to enter the car wash area. All of the equipment that you brought that was not double bagged is going to have to be left and washed. So the microphone you're recording me with right now, for example. And then we are going to strip off all of our mine gear and we're going to go through the shower procedure and get into the clean Tyvek suits so we can enter the lab. When we get into the lab though, you'll find it's air conditioned. And it's very bright, kind of like this, but the walls are a lot cleaner. And after a few minutes, you'll find it hard to believe that you're 2 kilometers underground.
Honestly, I'm sweaty enough I need the shower. I'm sad to tell you that they took away my mic for the showering, so no sounds from that. But when I get out, I enter the lunchroom first. And honestly, Mike is right. It doesn't feel like you're underground. It feels like you're in a generic, windowless lunch space. The walls are shiny and white. The ceilings are high. There's even coffee and Wi-Fi. But then you walk into where the experiments are taking place, and you're reminded, oh yeah, this is very cool.
Welcome to SNOLAB. This is where the magic happens.
We'll be right back. Okay, let me ask you a question. So how do you look for something you know nothing about? Here's how SNOLAB's Dr. Jody Cooley thinks about it.
So how do you cope when you've lost your keys in your house, right? You're like, okay, let me try to think. So if I lost my keys in my house, I might try to think backwards in steps of where was I last? And I would start eliminating, well, my keys aren't in the living room, my keys aren't in the mudroom, my keys aren't in the car, they're not in the garage, they're not in my bedroom, right? You would slowly work through your house until you found your car keys. So I would say, coping with looking for dark matter is something the same. Like we do have some idea of what dark matter might plausibly be. Like what is plausible mass for? What is a plausible interaction strength? So we start looking for plausible dark matter candidates in plausible areas, and then as we rule it out, we X that out and we go to sort of the next space. So I would say looking for dark matter is kind of like looking for your lost keys in that way.
There are 11 experiments that are either up and running or in the process of being built at SNOLAB. Some study fruit flies, some are looking for supernovas, but most are looking for dark matter. They have sci-fi sounding names like Sensei, Pico, and Deep 300. And one of the most sensitive dark matter experiments in the world is currently being built here. It's called the Super CDMS, which stands for Super Cryogenic Dark Matter Search.
Shall we head to Super CDMS?
Sure, yes, let's do it.
When we get to Super CDMS, it's still being assembled. Right now, it just looks like a very precisely measured round dance floor, built specifically to be in an active mine.
So this platform was designed specifically to decouple the experiment from vibrations in the mine. So we call it the seismic platform.
That's Dr. Andy Kubik. one of the research scientists working on this experiment.
If you look really close underneath, you can see that it's actually sitting on springs in the form of coiled wires. So those keep the detectors from vibrating if the ground does.
One of the most striking things about Super CDMS is the sound in the room. The looping nature of this mechanical sound almost makes it sound like we're in an underground rave. But really what we're listening to is the hard work of specialty fridges used to keep the experiment's sensors very, very cold. Here's Dr. Kubik.
That's like the way we'd like to describe it, is colder than space. Only the detectors have to be that cold, but a lot of the electronics have to be fairly cold as well, like liquid nitrogen temperature roughly.
Those detectors Dr. Kubik mentioned, they need to be cooled to almost absolute zero. I asked Ivan just how cold that actually is.
It's hard to think of absolute zero. I mean, on a temperature scale, it's minus 273.15 degrees Celsius, right? So it has a value. It's a very low temperature. That idea of being just a few hundredths of a degree away from absolute zero is going to take you to a point where the inner noise and the movement inside the detector is dampened out, and a passing particle like dark matter, if it interacts, would make itself visible. Super CDMS, it's got these wafers, these hockey puck size, a little bit larger than hockey pucks, discs of very pure metal, silicon and germanium, and you can almost imagine the atoms in these metal like a crystal lattice. So imagine this kind of lattice almost like bed springs or something just sitting there. And the idea is if a dark matter particle passing through comes close enough to one of the nuclei of the atoms in these detectors, it'll jiggle that atom, and the jiggle will kind of resonate through the whole crystal. But the trick with the detector is that etched onto the surface of these discs is this superconducting material that's just at the threshold where electricity can pass through without resistance. The idea is that one of these little jiggles would break that state. It's almost like, imagine a tiny little fly landing on a balance beam and suddenly shifting the balance. So then the trick is, well, how do you know if it was dark matter or something else? And that's where you start to have to accumulate statistics. You have to run the experiment for a long time, account for all the possible sources of jiggling, and see if there's something left over. So if dark matter is somewhere in the mass range of a proton or up to 10 times a proton, Super CDMS would be perfect for finding it.
But all of this equipment comes at a cost, $42 million specifically. Yes, that is a lot of money, but to put it in context, Elon Musk spent $44 billion on Twitter or X or whatever it's called now. So anyways, this experiment is being funded by the US Department of Energy, the National Science Foundation, and the Canada Foundation for Innovation.
This is a big bet, due to the footprint, the cost, and the investment from SNOLAB. For me, this is like so personally exciting to see this. Like this is like almost my whole career. Well, certainly my whole career since entering dark matter.
There is no denying the excitement in the room, even though this experiment won't be fully operational until early 2025. But people here are really hopeful that this project might be the one that finds dark matter.
I hope in my tenure as director here that we have another Nobel Prize for the lab. And I think if we had a positive detection and we were first in Super CDMS, I think a Nobel Prize would be on its way.
It wouldn't be the first one for SNOLAB. The facility's founder and principal researcher, Arthur MacDonald, won a Nobel Prize for his discoveries about how solar neutrinos behave. But even without the top prize in science, running these experiments gives Canada huge cachet, according to Dr. Cooley.
This is great for Canada. What we need to do now as scientists, as lab staff, as leaders in the field, is to continue to push the science forward so that Canada can remain number one in underground science. That's what we want. We want, when people think about doing underground science, we want them to think of us first.
But here's the thing. Even with equipment as sensitive and complex as super CDMs, there is no guarantee that the scientists at SNOLAB will succeed. I want to know, and this is not specific to SNOLAB, but as a scientist who's devoted their career to dark matter, what if dark matter is unknowable?
Well, that still tells us something. I think, this almost goes back in my head to like, why do you do fundamental science at all, right? We're trying to increase the knowledge, but to me, it's like not just the end of the journey, not just what is the answer at the end, but it's the entire journey and how you get there. So in getting to a point where we felt like, okay, dark matter, trying to know anything more than it works through gravity, okay, that would be extremely disappointing. But along the journey, I would think about all of the advances we had made. We have made huge advances in sensor technologies. We've made advances in computing. We've made advances in learning about different algorithms and data training. And so I think, trying to look at the endpoint, like it's always disappointing if you get there. But I think if you look at it as the whole journey and the whole collection of knowledge that you've gained along the way, the serendipity of things you might have discovered, those are the positive effects that you would have to take away from it.
Even though we're talking about physics, this story feels unshakably metaphysical as well. And it reminds me of Carl Sagan, the scientist who made the curiosities of the universe accessible to the general public.
This is where we live, on a blue dot. That's where everyone you know and everyone you ever heard of and every human being who ever lived out their lives. It's a very small stage in a great cosmic arena.
In one of his books, he says science is like a candle in the dark. Observation by observation, science is illuminating the world around us. Even when an experiment fails, the light from the candle gets a bit brighter.
I often think scientists must be the most positive people that I know, because the number of times that you fail at science before you succeed is remarkable. But these scientists, they don't just give up and throw their hands up in the air. They pick themselves up and they say, all right, what's next? Every failure to observe dark matter is an opportunity to think about how can we do it better next time.
That's it for today. I'm Menaka Raman-Wells. Our summer producer is Nagin Nia. Our producers are Madeleine White, Cheryl Sutherland, and Rachel Levy-McLaughlin. David Crosby edits the show. Adrian Chung is our senior producer, and Angela Pacenza is our executive editor. Thanks so much for listening, and I'll talk to you tomorrow.